So now that we have, sort of an introduction to what an atom is, as we said, once we get later on in this course, we'll get a much more revised picture of especially what the electrons look like. But we're now going to start looking at the periodic table. And for most elements, you know, we have some sort of symbol, and then we'll write them sometimes like this, with a superscripted number on the left. This is known as the mass number, and it's the number of protons plus the number of neutrons. And then we'll see sometimes a number down here, which is the atomic number. Which we'll learn is just the number of protons. In fact, as we'll see later on in this section, the number of protons will actually define what the element is. Now, note first thing, this mass number, it's always going to be a whole number. So it won't match the exact number that's on the periodic table, which when we look at that in a minute, you'll note are often to several decimal places. But two things that we can say right now. If we have a neutral atom, for example, carbon. Carbon is element number 6. That atomic number will tell us that carbon has 6 protons, and that we can say it always has 6 protons. If it has a different number of protons, it's a different element. If it's neutral, in order for the charges to balance, it'll have the same number of protons and electrons. The number of neutrons, on the other hand, can differ based on different isotopes. So for carbon, there's 3 common isotopes: carbon-12, which makes up most of the natural abundance of carbon, carbon-13, and carbon-14. Those are the three isotopes of carbon. They all have 6 protons. So if this number that we've written in here is its mass number, or is the number of protons plus neutrons, that means carbon-12 has 6 neutrons, 13 has 7 neutrons, and carbon-14 would have 8 neutrons. All right, so let's start by bringing up our periodic table. And we're going to come back to this, quite a number of times, especially in the next few minutes. And so the way this periodic table is set up, we have the element in the middle, we have the atomic number at the top left, and then we have a mass number. And you can see that for most of the elements, it's not a whole number. So why is it that that atomic mass is not a whole number? Well, that's because our atomic mass here is taking into account all of the naturally occurring isotopes. And so for carbon-12, carbon-12 has a mass of 12 AMUs. And we'll define what an AMU here is in a moment. But it is a very, very small quantity because, again, we're talking about the mass of exactly one atom. Carbon-13 has a mass of slightly over 13 AMUs. And carbon-14 has a mass of a little over 14 AMUs. Now, if we look at the relative percentages of these compounds, carbon-12 is almost 99% of the natural abundance of carbon. Carbon-13 is a little over 1%. And carbon-14, you can see, is a very, very small number. Carbon-14 is actually not a stable isotope of carbon, and over time will decay into other elements. And that's actually what we use carbon dating for. So before we talk about what we're going to use these numbers for, we should define an AMU. So one AMU is actually based on the mass of carbon. It's 1/12 the mass of a C12 atom. And if we want a number, it's approximately 1.66 times 10 to the minus 24 grams. Now, again, if we go back to our periodic table here, we can see that carbon is listed not at 12, but 12.011. And that's what's going to be true for all of the elements here on the periodic table until we get to things up into the 90s. What we can do is we can take a weighted average of the different isotopes of carbon. So 98.892% of carbon-12. And then just over 1% of carbon-13. In this case, we can ignore the carbon-14 because it is such a tiny amount that it won't have any impact on our calculations. And so if we do this, again, we're just doing a weighted average of the masses of the different isotopes. We get that number that we see on the periodic table. All right, so we'll now start looking at the periodic table itself and what happens as we change any of the other numbers of subatomic particles. So we've already seen that if we change the number of neutrons, we get a different form of the same element. If we change the number of electrons, we get what's known as an ion. An ion is a charged form of the element. And it comes from either gaining extra electrons or losing electrons. So for any element, we can figure out on average how many protons, neutrons, and electrons it has. So fluorine, again, we can go back to our periodic table. We can see has a mass of approximately 19. And so for what we're going to do, we're just going to round these numbers. So because it's atomic number 9, it has 9 electrons, 9 protons, and 9 neutrons. But what if we add an extra electron? So now we have 10 electrons, still 9 protons, and still 9 neutrons. Well, there's now one more electron than there are protons. And so because of that, this ion will have an overall negative charge. And that charge is based on the difference in the number of protons and electrons. Since there's one additional electron, this ion of fluorine will have a charge of -1. If we were to somehow add 2 electrons to something, and we wouldn't do that for fluorine, but if we went one element over to the left to oxygen, oxygen has 8 electrons, 8 protons, and 8 neutrons. So we could add 1 to it, but it turns out with oxygen it's more common that we would add 2 electrons and get 10 electrons, 8 protons, and 8 neutrons. Now we have a difference of 2 comparing our protons to our electrons. So the charge here for oxygen would be -2, or we typically write that as 2 minus. Because this is a negative ion, or both of these are negative ions, we would refer to these as anions. We can also go the other direction. Sorry, we're not getting a blank page here for some reason. So what if we lose electrons now? So this is something that we commonly see in an element like sodium. Sodium has atomic number 11, which means it's 11 protons, 11 electrons, and with a average mass of about 23, that means sodium will have 12 neutrons. But now we're going to take one of those electrons away, leaving us with just 10 electrons and still 12 neutrons. This means that our sodium, because it has more protons than electrons, is going to be positively charged. And for positively charged ions, we refer to those as cations. And if you ever have trouble remembering that, just remember that a cation is going to be positive.